Okay. So, may I lift the mask? Okay. So thank you very much for the presentation. I'm Gianfranco Julian. I'm a mineralogist from the University of Bologna. And thank you, Professor Aldre, for the introduction. Yes, today we're going to see some topics related to the crystal structure simulation methods with some examples in biomineralogy. Can you hear me from the virtual classroom?
Yes,
Stefano?
yes, it's okay. Thank you, Gianfranco.
Okay. So, let me see if I can. Okay, laser pointer, so you can see the laser pointer in case. Perfect. Okay, so my presentation is the outline of my presentation is here in this slide. So you can see that we'll start with some fundamentals on crystallography. Then we'll see some topics related to the infrared and Raman spectroscopy, some theory and some applications, obviously. Then a very brief introduction to theoretical methods, simulation methods that are employed in crystallography and in infrared Raman spectroscopy, and then some examples related to biomineralogy and mineralogy. Okay, so let's begin with the fundamentals of crystallography. Here you can see a picture. It is not here by chance. This is a diffraction pattern for this mineral here, that is halite, that is the mineralogical name of the tabletop salt, okay, sodium chloride. And this is a picture, one of the pictures that was recorded by the discoverer of the X-ray diffraction by crystals, that is Max von Laue, who won the Nobel Prize for this discovery. He developed an initial theory and formulation related to the X-ray diffraction, okay, but who are most famous for the development of the theory and description of the X-ray diffraction and determination of the crystal structures are William Henry Bragg and his son William Lawrence Bragg, that won the Nobel Prize the next year for crystallography, for physics, for the use of X-rays to determine crystal structure. And this is just a brief history of crystallography. Crystallography, as you can see from the years 1914, 1915, is a relatively young discipline, okay, modern crystallography. Then we had some other very important people who make important discoveries and won the Nobel Prizes for them. For example, Davison and Thomas received in 1937 the Nobel Prize for the diffraction of electrons by crystal, so electron diffraction. Dorothy Hodgkins is famous for the determination of several important crystal structure related to biochemical substances. Here I reported just one example, that is vitamin B12. And then obviously we have in 1962 Watson, Crick, and Wilkins, who won the Nobel Prize for the determination of the helical structure of DNA, a work that was pioneered by Rosalind Franklin. Then we have in more recent years Schul and Shetman for the first one for neutron diffraction in 1994, and in almost 11 years ago, Shetman for the discovery of the so-called quasicrystals. Okay, so the first question that would come up to your mind should be, what is a crystal? Okay, a crystal is, by definition, a solid material with a determined chemical composition. In mineralogy, we also say that it is determined but not fixed, because it may vary over some range of composition. Then this material presents a regularly repeating internal arrangement of its atom meaning that there is a high internal order inside the structure, and often presents macroscopic faces oriented in specific direction. Here I report in this picture some crystals related to fluorite. It is calcium fluoride. This is a mineral, with, as you can see, that presents a cubic faces, very nicely developed cubic faces. And here you can see the crystal, the atomic arrangement of the atoms inside the structure. Okay, in fact, as you can see, minerals are that are made in geological conditions, but also in biological conditions, represent the largest source of naturally formed crystalline solids. Crystals can also be, obviously, synthetic materials. So when we talk about the geometry of crystals, historically, natural scientists and crystallographers as the only instrument they write. So they had to study well-developed crystals, macroscopic crystals that can be found in nature. So they described the crystal, for example, here you can see a pyrite mineral, a pyrite crystal. They can see a very nice cubic faces, very cubic shape. And we can describe these crystals in terms of polyhedron geometry. So polyhedrons are described by faces, then edges, and vertices. Okay, and the other angles that are the angles described by the faces. There is this nice rule that is called the Euler Rule that states that the sum of the faces and vertices in a crystal is equal to the number of edges plus 2. You can do it by yourself considering the a cubic crystal, cubic shape. We have 6 faces, 8 vertices, and the sum so is 14. And there are 12 edges. 12 plus 2 makes 14. So this rule is satisfied. In crystallography, historically, there are 2 very important rules. The first one is the law assessed by Steno in the 17th century. That is the law of the constancy of the interfacial angles. This is the fundamental law of crystallography. It states that the angles between 2 corresponding faces, let's take this crystal as an example, of any solid, chemical or mineral species are constant and are characteristic of that species. It means that if you take, for example, in this case, a perfect crystal, perfect octahedral crystal, and that is made by a kind of material, for example, it could be pyrite, okay? The angle described by each phase is constant at specific temperature and pressure conditions. In this case, the mineral is perfectly octahedral. But in nature, we could find disproportionate crystals. No matter what, the angle between the same faces are constant. The angles are constant. Okay. And this applies to naturally occurring crystals and also to synthetic handmade crystals made by man. Then we have a second law that is called the Hawes law, that is the law of the rational indices. Okay, so remember, these laws were determined in a period where we do not have X-ray diffraction. We do not see the atoms. We see only a macroscopic object such as this one here. Okay. This law states that for a given crystal species, it is always possible to choose 3 vectors, A, B, and C, so that all the natural faces of this crystal cuts the length proportional to the 3 integers numbers. Okay? This is a way to mathematically describe how is the crystal shape. So let's take these 2 examples here. We have 2 crystals. You can see that there are different faces, and this is the polyhedron that is associated to this development. The idea of AOI is that the crystals are made by stacking elements. For example, in this case here, there are some very small cubes that makes the crystal. And if you stack these cubes, these small building units together, you can obtain different crystals with different faces. And then you can obtain different, different polyhedral shape. You can see, if you come to the Mineralogy Museum Bombici at the University of Bologna, you can see a real, touchable model of the AOI model, where you can see these small cubes that stacked in different ways describe different crystal shapes. Okay, and this is the first idea of periodicity. You have a small unit block that is repeated along the free Cartesian direction, the three-dimensional direction. So, when we talk about crystal geometry, we distinguish between two features. On one side, we have the morphology, that is also called the crystal habit, that is the external shape of the crystal. Here we can see a quartz crystal. Okay, you can see its shape. This is almost prismatic. And then we talk about the crystal structure, that is the ordered repetition of atoms, ions, and molecules inside the crystal. So on one side, this is a macroscopic property. The crystal structure is a microscopic, atomic scale property. Okay? In fact, you can distinguish between crystalline and amorphous material, taking, for example, silica. Silica is a CO2, okay, silicon oxide. It can be either crystalline at room temperature and atmospheric pressure. The stable phase is quartz. Okay, you can see here the crystal structure, where we can describe a long-range order of the atoms. It means that the atoms are regularly repeated along the three directions, the three-dimensional directions. And then we can describe an amorphous silica that is called glass, that is non-crystalline. And as you can see here, we do not have a long-range order. The atoms are not regularly repeated. We describe it in terms of short-range order. So there can be some degree of order, but only at short range between the different atoms. So we introduce some concept. We have to introduce a further concept, that is symmetry. When we talk about crystals, okay, I showed you a prism, a cube, different polyhedrons. So this mathematical object can be constructed considering also symmetry. Okay, symmetry derives from the Greek word symmetria, that is agreement, means agreement in dimensions, due proportion, and arrangement. So what crystallographers did in the past and today is to describe the shape of an object in terms of a set of mathematical rules. Okay, and we can express these rules in terms of algebraic formula or matrix representation. We will not deal with this representation in this lecture, okay? But I tell you just to know that these rules exist, okay? Obviously, if we talk about symmetry, what is the object with the highest symmetry is the sphere. Okay, the sphere is considered from a mathematical point of view the object with the highest symmetry. And then we say that any body, this object here, this laptop, this mouse, is said to be symmetrical when we can divide it into parts and that are related to each other in certain ways. These ways are the so-called symmetry operation. Okay. So we have, for example, if I take my cell phone, it is almost rectangular shape. If I rotate it by 180 degrees, you do not distinguish what I did. The object is the same as in the initial position. Okay, you do not, you cannot. If you close your eye, I rotate it and reopen the eye, you can see the object is almost identical to the starting point. Okay, so in general, successive application of a symmetry operation must ultimately bring the body, the object, into its original state again. Let's take some example from nature and from art. For example, a snowflake. A snowflake is symmetric. Okay, you can see here this object has a 6-fold axis of rotation, so we can rotate this snowflake by 60 degrees, and we cannot distinguish the original body and the rotated object. Okay, the original snowflake and the rotated snowflake. From architecture, the octagonal ceiling of the Ely Cathedral in England. Okay, this is an octagon. Okay, if you take an octagon and rotate it, so if you can rotate it 8 times, and you obtain always the same octagonal ceiling, the same object, an object that is indistinguishable from the original one. Also, obviously, we have the tile work and mosaic in La Alhambra, this castle in Granada, Spain. We can see here these patterns that are regular repetition of objects on lines and areas. A music score. This music score is symmetric. If you take this score and rotate it by 180 degrees, you can see here the key, the music key here. If you rotate by 180 degrees, this key goes here. So this object here is symmetric. It is attributed to Mozart. Okay, it is funny, but actually it is symmetric. Obviously, in nature, let's take an example from marine biology, bivalve mollusk shells. You can see here they are symmetric. There are mirror planes. Okay, they are specular. And obviously, from mineralogy, we have a mineral. Okay, I already talked about cubic and octahedral pyrite, but also other shapes are present in nature. So we already make this mathematical definition of symmetry. An object has symmetry if there is an operation or transformation, such as translation, rotation, or reflection, which maps the figure object onto itself. For example, if you take this butterfly here, we can draw a plane that crosses the butterfly in the middle, and you can see that this object is symmetric by a mirror. This half here is mirrored on the other side of the mirror plane. Let's apply this concept to crystallography and to crystals. Okay, when we talk about symmetry in crystals, we must introduce the so-called space groups, which considers that are a mathematical set of rules. We'll see some of them later. That considers 2 types of symmetry. The translation symmetry, okay, that is the shift movement along, for crystallography, 3 directions, for a certain specific distance, such as the operation does not result in any change of the shifted pattern. Translational symmetry is related to the pattern of repetition of objects in that 3-dimensional space. In crystals, we are obviously interested in 3D patterns, but we can see here an example of bidimensional patterns. For example, here you can see different kind of repetition patterns in the bidimensional space. And then we have point symmetry. Point symmetry is the mathematical group of isometries that keep at least one point of the object fixed. Okay. If I take, again, my cell phone, rectangular, I put the rotation axis in the middle of this object. It rotates. Every point changes, rotates, but the point where the axis of rotation axis crosses my object. Okay. This is the mathematical definition. Okay, let's start with the translational symmetry that historically is the most recent one. Translational symmetry was determined by X-ray crystallography. This is an invisible operator by the naked eye. Why? Let's take, for example, this cell phone. Does it have a repetition in the three-dimensional space? No. No. It means it is not repeated in space. It is an object. Translational symmetry refers to the atoms inside the structure, so something that is not visible to the eye. There are a lot, an uncountable number of atoms inside this cell phone. If it was a crystal, a perfect crystal, they would be almost infinite from our perception, and they are repeated in space. Okay, so the crystal from the X-ray crystallography and from the mathematical description is constructed by the infinite repetition in three-dimensional space, that is called lattice, of identical structural units that is called basis. So the crystal is the lattice, so the pattern of repetition in the three-dimensional space, and the bases that are the objects that are repeated. These objects in crystals are atoms, molecules if you have molecular crystals, ions, group of ions, okay? And the lattice is the translation, okay? The translation vectors A, B, and C. So the lattice is defined by the three translation vectors A, B, and C, and any point node in such lattice might be described by the vector R, that is given by the combination of these three vectors A, B, and C, and U, V, and W, that are the factors that multiply these vectors, are arbitrary integers. Okay, so the lattice here, for example, let's take this example in the 2D. We have two vectors, obviously, because we are in b-dimensional space. So we have A and B. You can see here this vector A. Let's take this node. These nodes here are separated by the A. So this node is repeated here, 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 here by A, translation of A, and in this direction by B. A and B describes also an angle that is called gamma. We'll see it later. So the crystal axis A, B, and C forms three adjacent edges of a parallelepiped, obviously. And the lattice translation is defined in this way. This is the mathematical operator that describes this translation. That is here reported, for example. Okay. These are the nodes. These black dots here. We can attach to these nodes these lattice points the basis atoms, okay, which are characterized by composition, arrangement, and orientation. The number of atoms that can be attached to each node can be as low as 1. For example, we can have here, instead of a dot, we can have an atom, okay. For example, an iron atom that is repeated in the three-dimensional space, or we can have a very big molecule, for example, proteins. One of the branches of crystallography is biological crystallography. That is to describe the position of atoms of carbon, oxygen, hydrogen. It is very difficult, but it can be described the position of the atoms inside a very big protein. Proteins, you know, can be made of thousands of atoms. And there is a whole branch of crystallography that is devoted to this kind of studies. Okay. Okay. Each atom, given the three-dimensional vectors, okay, A, B, and C, the position that is the center of each atom, for example, let's take again halite here. We can see different examples. We'll, for example, halite has a cubic structure. So A, B, and C, these three vectors describes a cube. Okay. The position of each atom is described by this relation here, R, position R, is given by the combination of the three vectors with X, Y, and Z being the so-called fractional coordinates. So we can describe, given the lattice, we can describe the position of each atom inside the structure, inside the lattice, by the so-called fractional coordinates. Okay, we don't use Cartesian coordinates, but the fractional coordinates. And these values, these X, Y, and Z, can vary between 0 and 1. Okay. So let's take it. Let's summarize this concept. So we have the lattice here, the b-dimensional lattice. Let's take the basis here, this duct. We apply the lattice and the basis, we sum them, and we can obtain the crystal. So here we have the repetition of ducts in the space. Crystals are made in this way. Okay. If you have any question, please stop me. Okay. Then, okay, we have these three vectors. These three vectors, A, B, and C, describes the unit cell, the so-called unit cell, the basic repetitive unit that is the basic unit, sorry, that is repeated in the three-dimensional space. This is the unit cell. The primitive cell, by definition, is that unit cell that contains exactly one lattice point. Okay, one dot. Lattice points at the edges of the cell are shared with each other cell. Okay, so they count as a fraction. For example, in this b-dimensional case, okay, the unit cell here is that one. For example, let's take this. If we repeat this object here, this this parallelogram here in 2D space, each dot here, for example, let's take this, is shared among 4 parallelograms. So this dot counts as 1/4. 1/4 plus 1/4 plus 1/4 plus 1/4 makes 1. Okay, so this is one lattice point. This is why we say that a primitive cell is one lattice point. Okay. This is the case of a b-dimensional lattice. In 3 dimension, each the edges counts for 1/8. Okay. For example, in this case here, this lattice here is not primitive. Why? Because you can see we have 1/4 here, 1/4 here, and here, and this counts as 1. But this dot here, if we repeat this lattice, counts as 1/2. 1/2 here, 1/2 here. So we have 2 lattice points here. So this is not a primitive cell. Okay, this is a generic unit cell. No basis contains obviously fewer atoms than a primitive cell. Obviously, okay, we have just one node. And by elementary analysis, the volume of elementary vector analysis, the volume of a cell is given by this relation. This is just to show you that there are several ways to describe, to define a unit cell. One of them is the Wigner size cell. That is a special type of primitive cell. It is the smallest one. Okay. Okay. So we saw the translational symmetry. Okay, translational symmetry. So the repetition of the nodes in the free space, the repetition of a pattern. We described a pattern in a three-dimensional space. Now let's see the point symmetry. So the symmetry of the object. Okay, the symmetry, for example, of the basis. Okay, this is the first kind of crystallography analysis that was performed in the past, starting from Plinius in Naturalis Historia and going to Steno and Hawi. Okay, so we have the analysis. The point symmetry is related to the analysis of the object. So, for example, the crystals, the macroscopic crystals that were observed by natural scientists. Example, sorry, the symmetry is the point symmetry considers the elements of symmetry that are points, line, and planes, and the symmetry operator that can be as simple as the identity, rotation, reflection, and inversion that are applied on the symmetry elements. So this makes the symmetry. Okay, let's take the trivial symmetry operation, that is the identity. Okay, here we have the space, okay, our object, the space, and here we have the element that is repeated by the symmetry elements. Identity, we have our duck in the center of this circle. Okay, the identity does nothing to our object. The object is still. Okay, let's take the rotation. The rotation is more involved. As you can see, the rotation can be proper or improper and occurs with respect to a line that is called the rotation axis. Okay, a proper rotation is performed by rotating the object by 360 degrees divided by n, where n is the order of the axis. Let's take this example here. We rotate, we have our axis, rotation axis, that is here where I placed the pointer, and we rotate this duck by 180 degrees here, and you can see that these two objects, if we rotate by 180 degrees, we obtain the same object. Okay, the object is this one, remember, the circle. What's inside the circle is our object. So this axis, rotation axis here, is 2, because 360 divided by 2 gives us the rotation, the angle of rotation. Okay. Here we have a ternary. This is called the binary rotation. This is the ternary rotation. You can see 120 degrees. C4, the 90 degrees rotation. You can see the rotation. Our ducks are placed according to this kind of rotation. The C6, okay, 6 ducks in our object separated by angular values of 60 degrees. Okay, so you noted that there were different symbols here. These are crystallography symbols used by crystallographers to describe, to show what kind of axis, what kind of rotation axis is present here. And you can see an ellipse for a binary axis, a triangle for a ternary rotation, a square for a quaternary rotation, and for a senary rotation or six-fold rotation, an hexagon. Okay. No, in crystals, obviously we can have, for example, a sphere as a rotation axis that is called C infinite, because we can rotate a sphere, a ball, by a a very small angle, and it would be always indistinguishable from the original object. But in crystals, in crystallography, these are the only allowed rotation axis, because otherwise we we would have objects that would not would not fill all the gaps inside our structure. Let's take this example here. The object, this is a pentagon, has a five-fold rotation axis. Okay, let's try to fill the gap, all the gap, so you can obtain a perfect fill pattern by repeating this object in space. As you can see, there is no way to place these pentagons in space without having these voids here. Okay, so this is not compatible to, this is a very simple explanation. There is a mathematical demonstration of this impossibility to have other rotation axis. This is a graphical representation of this concept. Okay. Reflection. Okay, obviously we have, in this case, we have a plane that acts as a mirror. So each point is separated, is reflected to the other side of the mirror. It says that you, for example, let's take the eye of the duck. The eye of the duck, the distance, the orthogonal distance with respect to the mirror plane is a certain distance. We go along the same direction, and at the same distance we should find the eye of the duck. Okay, this is the reflection. Okay, the mirror plane, this is called mirror plane. The mirror plane is called, labeled as M. Okay, here you can see, for example, you should know something from organic chemistry. For example, the chiral molecules. Chiral molecules, in this case, left-handed and right-handed molecules are symmetric. Chiral molecules are symmetric for a mirror plane. Our hands are symmetric for a mirror plane. It means that we cannot overlap the two objects. Okay. For example, these two ducks cannot be overlapped. Okay, in this case, the objects are distinguishable. So we have maybe racemic solutions of two chiral molecules. If the objects are, if the object is undistinguishable after applying the mirror plane, it means that the mirror plane passes through the object. Okay, this is typical of crystals. And the inversion center, in this case, we have a point. Okay, it is similar to in the concept from the mirror, okay, from the reflection, but in this case, the inversion is on one point. So, for example, again, the eye of the duck, we draw the segment linking the inversion center eye and the eye of the duck. If we prolong this segment at the same distance, we find the eye of the duck. Okay, this is called the eye, the inversion center, or -1, written this way with a bar over the 1. Okay, we can say, for example, here we have an example with two objects such as this one, or a crystal. Here the inversion center is inside the crystal, so we have an improper inversion. Okay. Obviously, we can okay, 5 minutes. Okay, until the pause. Obviously, we can combine this operation. For example, we can have the roto inversion. So it is an successive application of a rotation and an inversion, or a roto reflection, a rotation followed by a reflection. Okay, the roto inversion is labeled in this way, minus n, where n is the order of the rotation axis. For example, in this case, we have -4 roto-inversion axis here in this crystal. And here we have, or in this case here, and the roto-reflection is called Sn, or from the crystallographic point of view, n over m. For example, let's take the roto-inversion here. We have our starting object here, 1. We rotate by 90 degrees because we have a 4-fold rotation axis. Then we invert it and we go to 2. Then we rotate and invert and we go to 3. Then we rotate and invert and go to 4. Rotate again, invert, and we go back to 1. Okay? And for a 4-fold rotation here is, for rotoreflection here, you can see we rotate, for example, 1 to 2, and then it is reflected to 6, because here we have a mirror plane. This parallelogram here is a mirror plane. This is the combination for the point symmetry from the macroscopic object, but we also have the combination of the rotation and the translation, and we have the so-called screw axis. Okay, let's take it here, for example. You can see from the GIF here. And we also have the glide plane, that is the combination of a translation and a reflection. Okay. So here you can see we can translate from one unit. This is the translation, but here we have a 2-fold rotation. So this hand here is rotated, is translated by the half lattice vector, lattice translation, and then it is reflected. It is rotated. I cannot do the other way. It is rotated by 180 degrees, and then it is translated and again rotated by 180 degrees. Okay, we can make a pause here. Do you have any question? Is it almost clear up to now? Okay. I may pause the, I can, okay.
Okay. It's time to continue the lecture. Please take your seat. Let's continue the lecture. So everything was clear at the moment? Okay. So maybe one point that would be useful for you is to understand how and why all these operators and elements could be useful for you when you're studying crystals. Not just the mathematical information which is behind this object, but how you can exploit this information. Maybe Gianfranco, you can say that the crystal could behave
Exactly.
as a function of
different shapes, different crystals means that our crystal may behave according to the response when we investigate it. For example, by using different experimental methods, when we want to obtain something from our sample, it depends on these symmetry elements. Okay. For example, a cubic mineral, from an elastic point of view, when we make some elastic, give some elastic stimuli to the crystal, may behave in an isotropic way. Means that it doesn't change its response according to how I stimulate it. Okay, but for example, if I consider different crystal shapes, different crystal, for example, an hexagonal crystal, it presents some anisotropy. Okay, because it may, for example, give me a response, or it may grow in a different way according to the specific crystallographic directions. Okay, let's take an example from nature. I anticipate an example that I'm going to do later. Our bones are made of hexagonal hydroxylapatite crystals and proteins, that is a tropocollagen. Together, they response as an orthorhombic system. We'll see this difference. So the protein has a certain symmetry, has a certain behavior that depends. It's elongated, so we should expect a difference along its elongated axis or along the low dimension axis. An orthorhombic system is different. Hexagonal response, orthorhombic response, it is different. Okay, so we have some different behavior when we observe it. In infrared Rama spectroscopies. In infrared Rama spectroscopies, if your system has an inversion center, the signals related to the modes of vibration of your system, so the signals that you may expect from infrared or Raman spectroscopies, are highly affected, because if a mode is active in infrared, it is not active in Raman, and vice versa. If it is active in Raman, you will not find that specific vibrational mode in infrared spectroscopy. So the knowledge of the crystallography of your system, if you work with some crystalline materials, such as the shells of mollusk, or if you're going to study the bones of fish, you have to consider the crystallography of this specific material and expect a specific behavior from them. That is governed by the crystallography of it. Okay. I hope it answers this question. So we can make a summary of the symmetry the symmetry notations here. So we saw the mirror plane, the rotation axis, the rotoinversion axis, the rotoreflection axis, and inversion center for what regards the point symmetry. In space symmetry, we have obviously the translations, okay, the repetition of the pattern along the three crystallographic directions A, B, and C, and the combined operations that are the glide plane and the screw axis. Okay, just to know, from the crystallographic point of view, we consider the Hermann-Mugen symbols that are those in this column here. Schoenflies symbols that are those listed here are important for spectroscopy. Okay, they're used in different kinds of spectroscopies. This is something that you see in the crystallographic tables. Okay, for example, these are the symbols of the axis, of the planes, or the planes that are parallel to the plane of the screen, or this is the case of planes perpendicular to the plane of the screen or of your book. Okay, so we introduced the lattice, we introduced the basis, the point symmetry. So let's describe a little bit the so-called brevet lattice in 2 dimensions. Okay, so a unit cell is defined by, in this case, in 2 dimensions by 2 lattice vectors A and B, or equivalently by the length of these vectors, the moduli of these vectors A and B, and the angle gamma described by them. Okay, we can, given a certain repetition of nodes in space, in bidimensional space, we can choose whatever we like to describe a unit cell. Okay, we can take a big cell, a very small cell. The only important thing is that it has to be something that can be repeat our structure, our pattern in 2 dimensions in this case. Okay, so for a generic lattice, bidimensional lattice, we talk about describe it in terms of oblique lattice. Okay, that is this here. For an oblique lattice, we do not have any important relationship between the cell vectors. The length of these vectors A and B called, and the gamma angle described by them is here depicted. So we have the length is different, A is different by B, and their angle is different from 90 degrees. Okay, oblique lattice is invariant only under a rotation of 180 degrees or 336 degrees. That means identity. Okay, the other rotations, the 60 degrees, the 90 degrees, the 120 degrees, gives us some restrictions, some boundaries on the A and B vector. So, for example, if you take the 90 degrees rotation, we have that we must have our nodes placed in a way so that the length of the vectors is equal to they're equal, and the gamma angle described by the 2 vectors is 90 degrees. So we have the so-called square lattice. You can do the same things for the other reported here. So we have 5 in 2 dimensions. We have 5 possible brevet lattice that are the oblique, the square, the hexagonal, the rectangular, and the center of the lattice. Sorry, here the hexagonal gamma should be 120 degrees. Okay, not different from 90 degrees. It's an error. Okay. So to this one first. So we have, for a 3-dimensional system, we have to describe these lattice vectors. The lattice vectors A and B and C gives origin to the 7 crystal systems that are, considering the lattice parameters, for a 3-dimensional system, we have 3 vectors, A, B, and C. if we consider the different lengths of the vectors, we have three lengths, A, B, and C, the moduli of the vectors, and three angles described by them, alpha, beta, and gamma. For we can have a cubic system that is made by the lengths of the vectors are all equal, and the angles alpha, beta, and gamma are all equal to 90 degrees. We can have the tetragonal, it is a parallelepiped shape, the hexagonal. We have the rhomboedral or trigonal, the orthorhombic, the monoclinic, and the triclinic. So you can see here by looking at the axis system here that from the cubic is the most symmetric system because we have very tight constraints on the lattice vectors and the lattice parameters. If we go down, we have the tetragonal, hexagonal, rhomboedral. Two lattice vectors are equal, have the same length and describe two angles equal to 90 degrees. And whereas the third is different in length and describe a different angle. So this group is called the dimetric system. And the trimetric system, all the vectors have a different length, A, B, and C. An orthorhombic system has all the angles of 90 degrees. A monoclinic system, two angles are equal to 90 degrees, whereas the other one is different from 90 degrees. And a triclinic system is the least symmetric one, where we have all the vectors with different lengths and the angles all different from 90 degrees. Okay? From this 7 crystal system, and considering all the point symmetry compatible with this crystal system, we can describe the 14th Brevet lattices in 3 dimensions. You can see here triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, trigonal, and cubic. You can see there are different letters here before each crystal system. P stands for primitive, so you have one lattice point. You can see here the lattice points of in the cell. C means that there are a node on two faces that are perpendicular to the C-axis. So in this case, for example, for monoclinic, so it means that you have 2 lattice points. E means that the cell has a node in the center of the cell, so it is called a body-centered system lattice. Sorry. F means that all the faces have a node at its center, and R primitive. You have identical cell axis and angles. You have one lattice point, and it is specific to the trigonal case. Okay. So for this crystal system, from the point symmetry, we can describe by making different combination of the lattice vectors and sorry, not lattice vectors, of the crystal system and the isometries that the symmetry element operation that we made on the object. We have 32 crystal classes that are called the 32 point groups. Here you can see a representation of these point groups. We are not going to see them in details. If you go in any mineralogy class, you can see often you can see these tables on the sides of the classroom because they are used to teach this kind of information. And by combining the possible Brevet lattices with the point groups, the group of symmetry operation compatible with these Brevet lattice, we obtain for a b-dimensional case 17 planar groups, and for a 3-dimensional case 14 Brevet lattice combined by 32 group of symmetry operation. We have the 230 space groups. Let's take this example. This is in the b-dimensional case. What is the b-dimensional lattice of this wallpaper taken from Escher? Some of you, would you like to try to give me an answer to this question? What symmetry elements do you see? here. An inversion, who say that? Yes, an inversion center, a more macroscopic one. Yeah, of what angle? 90 degrees. Okay, so let's start by seeing that actually we have a rotation axis here. We have an inversion center here also. We have these lines here, solid lines means a mirror plane. We have a mirror planes here, 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 and here. We have these lines here that are dashed ones. They highlight the presence of a glide plane. So you have a translation and a reflection. Okay. So if we consider, for example, these 4 points here that are the points where we can see the rotation axis, we could try to draw a first unit cell that by translation creates our structure. Okay. But could you see the smallest possible object in this cell that may create our structure by symmetry elements? Yes. Yes. If you consider this object here, this square here, and you consider this the half of this square here, you have the triangle. Okay, you can obtain different. You can obtain the whole unit cell by applying to this object, to this repeating unit, this object here, the point groups, and then the translation. So we can describe the asymmetric unit and the unit cell. So the asymmetric unit of a space group is that part of the crystallographic unit cell which can be used to generate the complete unit cell by the symmetry of the space group. So here I took this for example, just to be a little bit greater in dimension. If we apply the rotation, we obtain the whole unit cell here. So the unit cell is the minimum portion of the space that can generate the complete crystal structure only by translation operation. Okay, so here you have your pattern. Your pattern has asymmetry inside it. Okay, so going quickly here, all of this information are collected in the so-called space group tables or space group diagrams. Okay, where you can see a typical lattice. For example, here you have the last symmetry that is the P1. You can see the lattice and some points, and the symmetry operator. Symmetry operator here reported in algebraic form. Okay, let's take, for example, the P-1. So it is the step further. You have an inversion center here and one symmetry operation more. We can go up in a monoclinic system. You can see that you have a lot of more symmetry elements and symmetry operation here listed, 8 symmetry operation. And then the last one here, an hexagonal system, okay, an hexagonal space group, P63M, okay, with all the symmetry elements and the symmetry operations that are 12. Okay, all of these are collected here in the International Tables of Crystallography. This is volume A. There are several volumes. If you're interested, you can go to them and have a look. So this is a description of the cubic lattices, just to take some examples. Okay, you can see here a face-centered cubic lattice. A face-centered cubic lattice is not a primitive lattice. The primitive lattice of a face-centered cubic lattice is the one reported here inside the cube. Can you see it? Okay, this is the primitive cell, the smallest cell that contains just one node, just one lattice node. An important feature, sorry, an important feature, it's an important concept that is used in crystallography, especially when we talk about X-ray diffraction that will be presented by Professor Valdré on the lecture of Friday, is the crystal planes that are determined by three non-collinear points. Okay, here you have the way to determine the indices of these 3 points. They are called the Miller Indices. So you find for each crystal plane of your interest the intercept of these points on the crystallographic axis A, B, and C. In this example here, you have the points 1, x1, 1, 0, 0, x2, 0, 2, 0, and x3, 0, 0, 3. Okay, these are the intercepts. So you take the reciprocal of these numbers, so 1 over 1, 1 over 2, 1 over 3. Then you reduce these integers to reduce these numbers to 3 integers having the same ratio. So you make the minimum denominator in common, and you obtain these indices here, 6, 3, 2. These are called the HKL indices, and the plane here is identified by these 3 indices in parentheses, 6, 3, 2. Okay. These are examples for in cubic crystals of crystal planes. If you have an index that is 0, it means that it doesn't cut the crystallographic axis. For example, this plane here, 0, 0, 1, doesn't cut the x and y axis. Sorry, it should be A, B, and C. So it doesn't cut doesn't cross the A and B lattice vectors, but only the C1 here. So it is 0, 0, 1. Okay. Okay. And crystal direction, we can also determine crystal direction, so vectors starting from crystal directions in the crystal, that they are identified by the so-called Miller-Bravais indices, U, V, W, okay, represented in square brackets. Please note that in a cubic crystal, if the U, V, W indices are equal to the HKL indices, the Miller indices of the planes, the direction is perpendicular to the plane. For other crystal systems, it may not be the same. It may be or not, depending on the crystal system. Okay. This is an example of crystal structures for halite. Okay, halite, sodium chloride, has an Bravais lattice that is face-centered cubic. Okay. The basis is represented by one sodium atom and one chlorine atom. The chlorine atom is at 0, 0, 0, the origin of the cell. The sodium atom is at 1/2, 1/2, 1/2 of the unit cell. Other important crystals. So here you can see the crystallographic cell. This is the primitive cell. Okay. Another important structure is the cesium chloride. Okay, it is a body-centered cubic. So here you have one cesium atom at 0, 0, 0, and the chlorine atom is at 1/2, 1/2, 1/2 in a cell. Hexagonal closed-packed structures. So we have different ways of arrangement of in the 3D space, three-dimensional space. So to minimize the interstitial volume, so we can obtain from the minimum volume, the minimum packing, we can obtain, for example, hexagonal closed-packed structures when we have the so-called AB. So let's take this example here, this picture here. The gray spheres are the A are centered on the A spots here. And if we want to put another plane of these atoms, it could be centered with centered on B or C. They are equivalent. So let's take it A and then B. The third plane could be over A, and so we have the AB, 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 AB repetition of planes, and in this case we have the definition of the hexagonal closed pack structure, or it could be the third plane could be centered on the C spot, the third plane A, B, C, and in this case it represents the face-centered cubic structure. Okay. A typical example is given by cobalt. Cobalt as a metal. Alpha cobalt has a face-centered cubic structure, so it has a ABC pattern of repetition of stacking of the planes of atoms, and epsilon cobalt instead has a AB structure that is hexagonal closed packet. Diamond, these are simple examples to show you that some minerals, some crystal structures may have the same repetition of atoms, but different atoms inside, obviously. Diamond and cubic zinc sulfide, that is called sphalerite or blend in from the mineralogical point of view, both have face-centered cubic structure, okay, lattice. The basis is given by two atoms, two carbon atoms at 0, 0, 0, and and the other at 1/4, 1/4, 1/4 inside the structure. And in zinc sulfide, obviously, one zinc, for example, is at 0, 0, 0, and sulfur is at the other position. This is a typical consequence of the directional covalent bonding. Typical examples are given by carbon, so diamond, silicon, germanium, and other minerals such as blend or silicon carbide. So here you can see the different primitive crystallographic cell. The stars indicate the atoms inside the primitive cell. Zinc sphalerite has a very interesting polymorph. That is polymorph means a mineral or a crystal that has the same chemical composition but different crystal structure. Okay, so zinc sulfide has two very important polymorphs that are blend, the face-centered cubic structure, and the hexagonal one that is called wurtzite. And you can see here the basis is given by two atoms, and it is given by a different stacking of the zinc sulfide atoms inside the structure. Here we can see these stackings. In cubic zinc sulfide, we have A, B, C stacking. In hexagonal zinc sulfide wurtzite, we have A, B, A, B. Okay, and this translates into different lattices and different crystal and different symmetry elements. For example, in cubic zinc sulfide, we have obviously it's cubic, the four-fold rotation axis, so rotation of 90 degrees. And also here you can see by orienting the crystals, we can see that there is a ternary axis, whereas the hexagonal zinc sulfide polymorph wurtzite has two ternary rotation axis and an hexagonal rotation axis, a six-fold rotation axis at the center of the unit cell. So it was anticipated by the question before. So why it is important? All of these features, all the crystallography is important because of different crystal structures means different properties, different directional properties. For example, this means anisotropy. Okay, anisotropy means that a physical properties that vary depending on the direction in which we observe it. Okay, Okay, for example, crystals, different crystals may grow in different ways, giving different faces, different shapes, according to the growth velocity of that faces. And this is related to, for example, the condition in which the crystal is forming, geological conditions of formation that involves the cooling of a melt, the magma, is different from the crystallization from solution. Okay, because, for example, if some adsorbent, if some molecules adsorb on a crystal face, on the nucleus of the crystal, it may hinder the development of that phase. So you can control the elongation, the shape of the crystal according to the need, and this is what nature does in a living system. The shells of mollusks grows in a certain way because of the interaction with proteins and the environment. Our bones are made. Our bones and teeth presents crystals that are elongated in different ways, that have different shapes according to the function that is in the body. Okay. So crystal growth velocity, piezoelectricity. This is an important. Property. So piezoelectricity is the transmission of charges of electricity according to the variation of stress inside the material. Bioelectricity, transmission of heat. Transmission of electricity due to the variation of temperature. Birefringence. So this is a crystal. So this is a calcite crystal that shows birefringence. So you have the variation of the speed of propagation of light inside a crystal. And we can also have elasticity and underderived properties. For example, the stiffness of a crystal. It depends on how you elastically compress a mineral, and the other derived properties such as the velocity of seismic waves inside the material. This is important for geology, but not only for this, because, for example, the elastic properties are measured by in crystals by measuring the seismic wave velocities inside a crystal. So you cannot, by reverse engineering, obtain the elastic properties of a specific crystals. Okay, and many other. Do you have any question? Okay, so I'm going very quickly on this topic here. Infrared Raman spectroscopies. Okay, so I would like to give you some hints about these important analytical techniques that can be employed in crystallography, and that uses crystallography as a basis for the interpretation of the results. So, infrared and Raman spectroscopy. So, to introduce this concept, where I have to make a very small review on the electromagnetic spectrum. So, an electromagnetic wave is composed by an oscillating electric field and an orthogonally oscillating magnetic field. This field, these electromagnetic waves, each wave is defined by a wavelength that is called lambda, and we can for electromagnetic waves, we can describe the frequency of oscillation of the field by using this relation that states that the frequency is equal to the ratio of the c, that is the speed of light in vacuum, over the wavelength. So, and the energy of a photon, so of an electromagnetic wave, electromagnetic waves can be interpreted from a physical point of view. In terms of a wave, or as a particle that is called photon, and each photon has an energy that is given by this relation here. So the energy of the photon is equal to the Planck's constant multiplied by the frequency, or equivalent to the speed of light divided by the wavelength, or by this term here, h, the constant, Planck's constant, the speed of light in vacuum, and the so-called wave number. The wave number is the inverse of the inverse of the wavelength. Okay, this is represented typically in reciprocal centimeters. Okay, this is a spectroscopic measurement unit. So, spectroscopies in general can be divided in three main types. Okay, that can be emission. So that when a material emits light when they are excited by other means that than the electromagnetic, than a photon. For example, it could be current, okay, electric current that transverse, or temperature. So we can describe these typical spectroscopies are of emission are catoluminescence of thermal emission, such as here. Then we have absorption spectroscopy. So the material may absorb a part of the electromagnetic radiation that hits them, and this could be both in transmission or in reflection. For example, this you can see here the colors of a glass window because of the light interacts with it, and you can see the transmitted light. And scattering, materials may produce a small perturbation of the radiation that collides onto them. So you can have elastic or inelastic scattering, and it can be, again, in transmission or in reflection. So let's go with the infrared spectroscopy. It uses the infrared light. Okay, infrared light was discovered by William Herschel. If we perform if we refract the sunlight, we can see the formation of a rainbow. Herschel noticed that below the red color there was something, because it put some water. Okay, he put a thermometer below in this infrared region below the infrared visible light, and he noticed that the temperature increased. And if we put the thermometer in between the incoming infrared light and the thermometer, we put a water cuvette, he noticed that the temperature of water increased, and the temperature measured by the thermometer was less. So infrared light was absorbed by water. This is an hint that infrared spectroscopy is an absorption spectroscopy. Infrared light from in the electromagnetic spectrum goes from about 2,500 nanometers to 25,000 nanometers. Converted, this is wavelength, converted in wave numbers, it means that it goes from 4,000 reciprocal centimeters to 400 reciprocal centimeters. And this is the typical frequencies or energy of vibrations in molecules and solids. Very briefly, we can describe these, the atomic vibrations. Okay, so we are infrared Raman spectroscopies. Very briefly, investigate the modes of vibrations inside your material. That could be crystalline or non-crystalline. Okay, it can be molecular, gaseous, liquid, or solid, amorphous, or solid crystalline. Okay, it can be used for several kinds of materials. And this method is investigate, gives you an information on the vibrational modes of your material. So vibration, what is a vibration? An atomic vibration. Atomic vibration, by considering a very simple example, could be if we take two atoms, okay, with mass m1 and m2 connected by a spring, this represents to a system that may oscillate if we give some energy to it. Okay, this is a vibration. And we can approximate, if as a first principle, as a first approximation, the so-called harmonic approximation, we can say that the atomic bonds between two atoms are the springs that connect these two masses. Okay, and we can describe it by the Hughes law. Okay, so the frequency of oscillation is proportional to the is directly proportional to the strength of the spring, so the strength of the bond, and inversely proportional to the mass connecting the masses. So if the spring constant is if the bond is strong, the frequency of vibration is high. If it is low, obviously the frequency of vibration is low. And if you increase the mass of the atoms or of the spheres, you reduce obviously the frequency of vibrations. This is the representation of the Hughes law for a potential, for a generic harmonic potential. Okay, so you here you have the system at equilibrium. You compress the spring, so you go at, for example, this is R0. You compress your spring, so you go higher in energy. If you expand, from the equilibrium, you go again higher in energy. It is a parabolic expression of the potential energy. However, we are talking about atoms, and for atoms we cannot use an harmonic potential. Why? Because when we talk about atomic systems, we have to change from classical mechanics in physics, classical mechanics, to quantum mechanics. So the energy levels are discrete. Here, in harmonic potential, you can describe any states in this potential curve. In quantum mechanics, you describe these energy levels. Okay, this is the so-called quantum harmonic potential. And the separation between the levels, let's say that this is the ground state energy level. Okay, the frequency vibration energy level 0, the ground state. The separation between the energy level is called a quantum. Okay, a quantum of energy, that is h, the constant Planck's constant, multiplied by the frequency. And the energy of these levels are given by n, an integer number, that is this one, plus 1/2 this frequency. Okay. En is the vibrational energy of the nth vibrational level. So this is a graphical representation of this difference. In a real world example, here we have the sphere that oscillates along the spring. You can see here the variation of the energy. Here we have a hydrogen chloride system. They oscillate, but they have the same energy. Okay, they do not change in this way. If we increase the energy, the vibrational level, energy level, so we provide, for example, energy to our system, we can see that it will go up in this ladder of energy level. This is a more realistic representation of the atomic vibrations in materials, because it is called the quantum anharmonic potential, because it is a Morse potential. If we increase the distance between the atoms at a certain point, we break our bonds. Okay, and this is what happens here. We have a bond dissociation at a certain length. Okay, but in this case, we have to provide a very high amount of energy. Okay. So this energy, the separation of these energies is, remember, h multiplied, the Planck's constant multiplied by the frequency. And this, the separation of frequency levels is in this energy range that translates into the infrared light region. So let's go to this slide here. It is a specific, remember, your system cannot acquire all the energy level between between two levels. To jump to your system, to jump from one vibrational level to the other, must acquire the specific quantum of energy. So it is a specific amount of energy that your system has to acquire to increase its energy level. So if the energy of the incoming radiation is not equal to this h multiplied by frequency term, you do not, the infrared radiation is not absorbed. Virtually, you observe this is transmittance, means you measure in infrared. I have my sample, I have my my infrared light that goes through it, and I have a detector here. So I measure the light that goes to my detector. This is the so-called transmittance, the amount of infrared radiation that goes to my detector. If the radiation does not have the energy necessary to the transition of energy level, of vibrational level, the radiation goes straight to the detector. So I have a 100% transmittance. If it instead absorbed, because the energy is equal to a quantum of a vibrational level, I have a reduction of the intensity of that radiation, and I see this kind of peaks, downward peaks in my spectrum. Okay, this is called spectrum as a function of the wave number. So we can express the spectrum as a percentage transmittance or equivalently as absorbance, that is given by this expression. This is a logarithm of the intensity. Okay, the question is, how many peaks should I see in my spectrum? Okay. The question is simple because I have many atoms. Okay, I have many atoms in my structure. I have many springs connecting my atoms inside my structure. So, in a molecule, I have, in general, from this perspective, I have 3 times the number of degrees of freedom in my system is given by 3 times the number of atoms. For example, water molecule has 3 atoms. I have 3 times 3, 9 degrees of freedom. For a molecule, for an isolated molecule, I have 3 translation in space. So 3 degrees of freedom are taken by translations in space. 3 rotations along the 3 axes. So other 3 degrees of freedom are taken away. And I have 3n minus 6 vibrational modes. If the molecule is linear, it is 3n minus 5. Because one rotation is equivalent. You see, a notation of symmetry. If I take this object here and I rotate in this way, I see a difference. But if I take this object and rotate in this way, this bottle, a cylinder, rotate in this way, do you see any difference? No. Okay, so this rotation does not have any degree of freedom associated for a linear molecule in this case. For a solid, I have 3 acoustic modes that are not visible in standard infrared spectroscopy, and 3n minus 3 vibrational modes that are called in solids phonons. Okay, the vibrational modes have this representation. They can be different ways. These stretching modes that are stretching of the springs, okay, between 2 atoms, and bond length variation, or bending modes that are variation of the bond angles. In this case, the spring is the angle, okay, and it can be scissoring, rocking, wagging, twisting. Okay, you can see that the energy of these modes from the bending modes increase towards going up to the stretching modes, and so also the wave number. Okay, so you may expect for your system that stretching modes are at high wave numbers, whereas bending modes are typically at low wave numbers. Okay, there are selection. Okay, so these are the theoretically available vibrational modes. Okay, for solids and molecules. How many peaks, how many signals may I observe now in my system? Okay, so an infrared mode is active, so it can be excited, it can be measured in infrared spectroscopy if during the vibration the displacement of atoms must change the dipole moment of the system. And the only allowed transition are those that involves the variation of a vibrational energy level of 1 + 1 or minus 1. These are the so-called infrared selection rules. So the dipole moment, very briefly, is a vector. Okay, is a vectorial quantity that is related to the electric dipole in your system. So it is due to the non-uniform distribution of positive and negative charges in your system. Okay, so this is a very simple example for hydrogen fluoride. The dipole moment goes from the positive atom to the negative one. Hydrogen is positive, fluoride is negative. So you have the dipole moment mu here, and you can see that if we stretch and compress the bond between hydrogen and fluoride, we can see that this vector changes. Okay, changes in length. So there is a variation. So this moment is the stretching mode of hydrogen fluoride is active. How many vibrational modes has hydrogen fluoride? It is a linear molecule, 2 atoms, 3 times 2 is 6. It is linear, minus 5, 1 vibrational modes, the stretching modes of the stretching mode of between fluoride and hydrogen atoms. So in an homonuclear molecule, such as oxygen, you do not see the signal because there is no permanent dipole moment, so you don't see anything. Carbon dioxide, you have a permanent dipole moment. It is linear, so you have again 2 atoms, 1 vibrational mode. Carbon dioxide is interesting because you have 3 atoms. It is linear, so 3 times 9 minus 5, 4 modes that are here represented. And you can see that these are active. The bending and the asymmetric stretching are active, but the symmetric stretching of the carbon and oxygen bonds, symmetric in this case means that they elongate and compress at the same time in a symmetric way. It is not active because here we have the dipole. You can see here the dipole moment goes here and goes on the other side. So if we stretch, the sum is 0. If we stretch the same quantity, it's again 0. If we compress, the sum, the vectorial sum is always 0. So this mode is inactive. So if you see a lower number of modes, it could be related to this feature, to the absence to the non-respectation of the not satisfaction of the selection rules. This is an example for water molecules. Sometimes you may see a lower number of signals, not because of the not satisfaction of the selection rules, but because some modes are degenerate. It means that you can excite them with the same energy, and they appear at the same frequency in your spectrum. For example, consider this bending. It is like bending on one plane the molecule, and the bending the molecule, and the bending the carbon dioxide on a perpendicular plane. Is it different by symmetry? No. I rotate it by 90 degrees. They are related by symmetry. So they have the same energy. They are called degenerate, and they appear at the same position in the spectrum. If you find a way to remove this symmetry, you may see 2 modes, separate modes. So this is typical the scheme of infrared spectrometer. I'm not going to in detail into this part. Let's see. Okay, the important thing here is that is this one. infrared spectroscopy is highly sensitive to the atomic masses, okay, and the bonds between the atoms, the kind of bonds. For example, in organic molecules, if you are interested in analyzing proteins, here I report an example regarding organic molecules. You can see here a triple bond between carbon, carbon, and carbon and nitrogen. This triple bond is different from this one, okay? And you can see here there are some bars. It means that these modes may appear, may fall, it is called, at different wave numbers, at different frequencies, because of the different chemical environment in your system. Okay, it is the vibrational modes are highly sensitive to the chemical environment. Each vibrational mode is highly sensitive to its chemical environment. For example, if a protein is stretched, completely stretched, or it is folded, some bonds may feel the effects of other near bonds. So the vibrational modes may fall at some different wave numbers. So there is no specific frequency. Carbon and hydrogen stretching modes fall at this frequency. No, it falls at a certain range of frequencies. Okay, it is your duty to interpret the spectra either by previous experimental determination or simulations, as we'll see later. I guess that we can make a 5 minutes break. Okay. Yes. If you have any question, please ask me freely. Okay. No.
Okay, we can continue that.
Okay. So. Okay, so we saw the bands. So when you obtain a spectrum from your sample, you can see different bands, different signals, and what you do is actually assigning these bands to specific modes to investigate, at least qualitatively, your sample. This is for organic molecules, but we can say the same thing to minerals. Okay, this is an example in of different functional groups or molecular motions in different kind of minerals. You can see here the carbonate ion CO3 in sediments, and you can see here that these modes may fall in this range here, but in minerals it is different. You can see by almost 700 reciprocal centimeters. So you may have a very different behavior of your system. And here in calcite, look here, calcite, you have the stretching modes of the carbonate groups, the carbonate ion groups. You can see varying from 1600s to 1300 reciprocal centimeters. Okay. So just to show you, this is an example of an infrared spectrum obtained for polystyrene spheres. Okay, this is polystyrene. This is your molecule, your system, and you can see a very high number of signals here below 1000 reciprocal centimeters. You have the so-called fingerprint region. It is important for the assessment of the molecule, for the organic molecule in your system. Then you have different modes. For example, the aromatic CH stretching. Aromatic CH is this here. It is not represented. Between 3000 reciprocal centimeters and 3061 reciprocal centimeters. The CH2 stretching, this one here, in this range here, and the deformation of the CH bond and aromatic CC bonds in this range here. And this is for quartz. Okay. The data here was taken from the RAF database. Okay, you can find online. You can see the main signals are the asymmetric stretching of the silicon-oxygen groups here between 1200 and 900 reciprocal centimeters here. The symmetric stretching in this region here, and the asymmetric silicon-oxygen bending modes in this region here below 600 reciprocal centimeters. Okay, and this is for calcite. Calcite, calcium carbonate. Okay, so here you have the calcite spectrum here. This is the structure of the mineral. What you see actually, what you investigate is are the molecular groups, the carbonate ion groups. And you can see here that the asymmetric symmetric CO3 stretching modes is at 1400 reciprocal centimeters in calcite, in mineralogical calcite. If you consider here, this is ACC, stands for amorphous calcium carbonate. So this is amorphous, it is an amorphous material, and you can see that the same signal falls at different wave number. Here it was about 1400 reciprocal centimeters. Here it is 1460 reciprocal centimeters. So you have a shift in frequency. Depending on this depends on the chemical environment. Different chemical environment, different arrangement of the atoms in the structure. Okay. Very briefly, the Raman spectroscopy is closely related to the infrared spectroscopy because it investigates too the atomic vibrations in materials, solid, gas, and liquids. But it is based on a different physical effects. That is the so-called Raman effect, that is the result of the inelastic scattering of photons from the sample that is irradiated from monochromatic light. You can see here the difference. In infrared spectroscopy, you send a lot of wavelengths to your sample, and you see which ones are absorbed by your sample. Here, instead, you send a specific wavelength, okay, a monochromatic light, a single wavelength, and you see what happens. What happens to your sample? What signals are emitted for your sample? Because when a monochromatic radiation hits a sample, you can obtain absorption, as in the case of, for example, infrared spectroscopy, or transmission. It transverses your sample, your matter, and does interact with it. Or it can be reflected or scattered, so diffuse in your in your sample. Basically, what happens is represented here. You have your sample molecule. You have your incident laser with a specific energy E0, initial energy E0, that is related to the wavelength of the laser that you employ. So you obtain an elastic. You may obtain, for most of the cases, elastic scattering. Namely, your radiation interacts with the sample and is re-emitted by your sample with the same wavelength, so the same energy. This is called the Rayleigh scattering effect. But a very tiny fraction of this incident light may be inelastically scattered by your sample. One photon every 1 million photons that interacts with your sample is inelastically scattered with a different energy, E, that is different, that can be either greater than the incident energy or lower than the energy of the monochromatic light. Okay, and this is the Raman effect. The Raman selection rules are different from those of the infrared spectroscopy. Okay, they involve the polarizability instead of the dipole moment of your system, molecule or solid, and you have that. To be active in Raman, your vibrational modes must change the polarizability of the molecule in your system. Polarizability is a tensor quantity, so it depends on the direction you excitate your sample. You invest your sample with your monochromatic light. So we can again see a correlation with the crystal systems. Okay. And describes the tendency to be polarized by an electric field. Remember, an electromagnetic wave has a component that is an oscillating electric field. Okay. So this is the relation. The induced dipole moment, that is the difference in dipole moment, is equal to the electric field and to the alpha, that is the polarizability of the system. This is the representation. These are the equations employed to describe the variation of the dipole moment according to the incoming electric field and the polarizability. Polarizability is this tensor, second rank tensor. It depends on the free direction x, y, z. Here we have the derivation of the Raman signal from a classical point of view. Very extremely briefly, it involves the oscillation of this electric field and the interaction with the motion of the atoms inside your structure. So the motion of the vibrational frequency may interact with the electric field from the incoming monochromatic light, and what you see is this final equation here. Okay, you can see, you saw all the derivation of the formula. You arrive to this final equation, where you can see that the signals that you obtain at your detector are given by the incoming Rayleigh scattering. So the incoming, you obtain a signal related to the energy of the incoming photon. So this is the elastic scattered photons, and two terms related to the inelastic scatter, where you can see here, this here is the frequency of vibration of the frequency of oscillation of the electric field. Here you see the frequency of the oscillation of the electric field minus the frequency of oscillation of the atoms, and here plus the frequency of oscillation of the atoms. So you obtain two signals: the Raman scattering with Stokes lines and anti-Stokes lights. From a quantum mechanical point of view, it is kind of it can be described in this with this simple scheme. When you have a radiation that interacts with your sample, it can be either absorbed as infrared absorption. So here we have the absorption of the amount of energy. However, the lasers that are employed in Raman spectroscopy are not infrared lasers. Some are mostly visible lasers with higher energies. Okay, so what actually it can be simply depicted as an excitation of your system from a ground state to a virtual energy level, okay, that is below the electronic transition levels. I'm not going into details into this matter. However, they are below the electronic excitation of your sample. You go to a virtual energy state. Your system here goes to a virtual energy state due to the interaction with your sample with a monochromatic light. Then it remits a photon with the same energy. So your system jumps to energy level and goes down to the same vibrational energy level. What happens here is your system acquired the energy from the incoming light, then it remits a photon with a negligible variation, or a small variation of its energy, because it goes to a increased energy level. Okay, so you can see that what we can see here is that we measure this difference. Okay, if you make the difference between the incoming energy, the energy of the incoming light, and the energy of the emitted photon, you can do by some math, and you can obtain the energy of the quantum energy for the excitation of that vibrational level, as in infrared spectroscopy. And the anti-Stokes Raman scattering, that is, you emit a photon with an increased energy level, increased energy with respect to the monochromatic light, is that because your system may be in an increased energy vibrational level, so it acquires the same amount of energy as in the case of in the previous case, and when it falls down, go back to the unexcited, it emits the photon to go down. This photon is emitted with an energy that is the sum of the incoming energy and the energy of the vibrational level. So it has an increased energy. Okay. Okay. The intensity of the signal is dependent. The intensity of the Raman signal is dependent mostly on on this formula. Okay, where you can see that the intensity of the signal is inversely proportional to the wavelength of the monochromatic light source to the fourth power of the wavelength of the monochromatic source. So if you reduce the wavelength, you increase the energy of your monochromatic source, you increase the intensity. But you have to pay some attention, because too energetic monochromatic light may damage your sample. Okay, and the other important, this is more technical, the other important parameter regulating the intensity of your signal is that it is maximum when your detector is placed at 90 degrees. This is sin theta, sin phi, sorry, as 90 degrees with respect to the direction of direction of the incoming light. So you should have a maximum intensity when the detector is orthogonal to the placed orthogonally to the direction of the monochromatic light. Your spectrum, the Raman spectra, is obviously different from that from the infrared spectroscopy, because here you have a very broad signal centered on the wavelength of your laser. Okay, it is due to the Rayleigh scattering. Okay, and then you obtain a symmetric peaks with respect to this the Rayleigh scattering peak that are the Stokes line and their anti-Stokes line. So the Stokes lines are those related to the photons emitted with lower energy than incoming ones, and conversely the anti-Stokes one have a higher energy. Generally, at ambient conditions, the Stokes lines are more intense than the anti-Stokes lines. Why? Because at low temperature, at ambient temperatures, it is more probable to find your system at a low vibrational level. Okay, at a starting low vibrational level. Sorry. So to compare, so actually the difference between the frequency or wave number or the wavelength of your peaks here, Stokes or anti-Stokes, and the Rayleigh band is equal, thanks to the graph that we saw before, is equal to the vibrational levels, vibrational frequency of the molecules of your of your system. Okay, of the vibrational frequency of the atoms inside your sample. So you obtain a signal, information that is comparable to that coming from the infrared spectroscopy. Some information that you can obtain from the Raman spectra is that, okay, you can obtain, particularly for crystals, the width of the peak is proportional to the degree of crystallinity of your material. So you can obtain some important information in this term. If your peaks are very sharp, your material is very crystalline, is highly crystalline. If it is broader, you may have some defects, or you may have a lower degree of the crystallinity in your material. The position of the peaks is obviously controlled by the chemical environment of your system, but also to the stress, okay, that are stored inside your solid. For example, if you have your atoms that are brought nearer, you are changing the environment of your atoms, so there may be an increase or decrease in interaction, and your peaks may be shifted in frequency, in wave numbers. And the height of the peaks obviously is related to the concentration of the substance and to the orientation of your sample. You can see here, for example, the signal centered at this point. If you make a tensile stretch, so you are stretching your material, the shift is going down in frequency in the wave numbers. If you compress your material, it may go up in frequency. It is not a general rule. Some modes may be shifted in the opposite way. Okay, you have to study this kind of information. So I introduced it before. So here you have the relationship between Raman and infrared. Okay, if your system has an inversion center, you have the so-called rule of mutual exclusion that says that if a molecule or crystal possesses an inversion center, then there cannot be normal modes, phonons, that are simultaneously active in both Raman and infrared spectroscopy. Do you remember the carbon dioxide infrared spectrum? We had two peaks because we have the asymmetric stretching, and the second peak is due to the degenerate bending modes in the molecule. We had a fourth vibrational modes, okay, that it wasn't active. The carbon dioxide molecule has an inversion center corresponding to the position of the carbon atom. So the only active mode in infrared spectroscopy, in Raman spectroscopy for carbon dioxide is this signal here for the symmetric stretching of the carbon-oxygen bonds. Okay, so this is important to know what kind. It is very important to know the symmetry of your object and how may your sample or your environment affect this symmetry. This is a typical benchtop Raman instrument. There are also other configurations, such as a confocal Raman microscopes, where a confocal microscope is associated to a Raman spectrometer to have a map of the Raman signal, to collect a map of the Raman signals within your sample by both XY. You can make XY maps and also Z stackings, so you may reconstruct the Raman signals coming from your sample. Typical light sources, as I told you, are obviously monochromatic light. We have different wavelengths. For example, ultraviolet lasers in these of these two wavelengths. Argon lasers with more or less green lasers. Helium neon lasers, they are red lasers, and near infrared lasers that are given by this material here. It is important. Yes? Which is the size of the sample? It depends. It depends. The size of the sample affecting. Sorry, I cannot hear the question very well. No, no. Typically no. It depends on what your sample is made, what is the texture of your sample, but the size, no. The size may affect your analysis. Well, if you have, for example, a confocal, if you work on a confocal Raman microscope, you may have limited dimension, for example, in the Z direction, because you have the optics here. For example, here you have the optics. If it is too tall, too high sample, you cannot work with it. But no, on the results, it depends. The results are dependent on what is what your material is made, how the material is oriented. So, because you have polarizability that is a tensorial property, so it depends. The signals may vary in height, not in position, in height due to the different crystal orientation. And it depends on the choice of the laser, not for the position of the peaks, because usually what you do is you center your spectrum on the laser on the laser wavelength. You convert it into wave numbers, so you have a Raman spectrum that is comparable to the infrared spectrum. So your zero of the spectrum is the wavelength of your laser, so it doesn't affect. But the choice of the laser, you see in the next slide, affects how your spectra appear. For example, okay, I told you, okay, the intensity of your spectra.
So along your sample, there is no absorption of light.
So along the direction. Yeah.
If you have, for example,
Materials.
This is not perfect because you don't have absorption on it.
No. No. You do not have absorption. Okay. You are thinking about the transmission of the signal. So you have your laser that hits your sample, and you think that you thought that the detector is below the material. No. Exactly. The question is no. I use the my sample, my detector. My sample is here, but the surface of the sample is here. I have the detector, for example, for a confocal Raman microscope in this position. So I'm collecting the signals that are scattered outside the material. Okay, or for there are some kind of transmission. There are transmission Raman spectrometers, but in this case, the signals are collected. You have your signal, your ray that goes through the sample. There are diffusion because the diffusion of your scattering, elastic scattering of your light inside the material, and you collect it at 90 degrees. So in this case, you have the highest intensity for other. This is not backscattering. No, and if you have in this position, you have no absorption. You have to be in. You have no intensity in this direction. In the direction of propagation of the light, you have no intensity because this formula here. You have the sign of the angle between the incoming light and the position of the position of the detector, the direction of the detector. So if you have a backscattered or in transmission, you do not have signal. So you have to put your detector on the best position would be on 90 degrees. In other configurations such as confocal Raman microscope, you have to collect your signal in different ways. Okay. Is it clear?
Yeah.
Okay. Okay. So this is a tabletop. Okay, the laser. The laser is a very important factor choice because on one side we increase the intensity of the signal, but it may, depending on your material, you may excite it electronically, so you may obtain the so-called fluorescence. For example, this is the molecule of interest that is to be analyzed by. This is indigo. This is organic molecule of organic pigment that is that wants to be analyzed by Raman spectroscopy. If I use a blue laser, okay, if I remember well, I obtain this kind of signal. I see nothing. This is fluorescence. I have no information on my sample. I may also damage my sample. Okay, so if I use a near infrared monochromatic light, I observe the spectra of my molecule with a very low background. Okay, so this is a summary table on the two properties of the two spectroscopies. Infrared spectroscopy is an absorption spectroscopy. Raman spectroscopy is a scattering spectroscopy. Okay. Very briefly, some notes on simulation. Yes. Depends on the configuration. Typically, it is fixed. If I remember well, I'm not aware actually of instruments with movable detectors, if not custom-made systems. Commercial systems, I guess they are more or less fixed.
They are optimized for the best detection of the system.
Yeah.
And in some cases, you can use polarized light. If you use polarized light, you have fixed the direction of the electronic vector of the light. And then you can rotate your crystal with respect to the fixed position of the electron. So you can see and look. And then the detector is optimized for the best signal in terms of intensity.
Okay, some few words. Any other question? Okay, few words on simulation methods. Okay, so I'm typically working with both experimental and theoretical methods that employs simulations. Okay, simulations is a research or teaching techniques that tries to reproduce an event that happened in the real world, okay, under test conditions, using some mathematical rules and physical rules that describe what happens. Describe what happens in the model that wants to reproduce a real world examples, okay, real world experiment. And typically they are made by computers, okay, or large scale facilities such as high performance computing. Okay, this is a case, a simulation. This is a real world wind tunnel test for an airplane. So you put your airplane in a wind tunnel and you measure the airflow through it, or you can make a virtual wind tunnel test with a reproduction of your system and study what happens to the airflow. Okay, the simulations can be used to predict, describe some phenomena or predict some effects. The simulation methods, different simulation methods for different kind of systems and times. Okay, we have this kind of representation of the models that we want to describe. If you want to study, for example, very large systems, we can use continuous simulations or engineering components or finite element modeling. Okay, if you want to study atomic scale events, we have to go down in this line. We have to use other theories. If you go to atomistics and molecular modeling, we are in the borderline between quantum mechanics and classical mechanics. So we have description of atoms as charged spheres. Okay, this is a field of force fields or something near it. If you want to simulate the electron, the nuclei, and the electrons inside our material, we have to go with no doubts with ab initio and quantum mechanical methods. Okay, so the system, if you want to describe a system, we have 4 information that we need. So the system description, so what and how many are the fundamental units of particles. The system condition, where are the particles in the space and what are their velocities? Okay. Are they moving? Are they still? The interaction, what is the mathematical form for the forces that are acting between the particles? So how can we describe interaction between these particles? And the dynamical equation, what is the mathematical form for evolving the system in time? Okay, if we are interested in seeing what happens in time. So we put all this information together, we run the simulation, and we obtain some results. The systems depends, for example, if you can see the smallest particle that, as I anticipated before, describes the physics behind it. So you have different physics, different theories and formulations for nuclear electrons, atoms, grains, and macroscopic components and so on. In atomic scale modeling, we can distinguish between zero-dimensional systems such as molecules, small molecules and macromolecules, polymers, nanotubes, surfaces, and crystals. Okay. To describe a mineral, from a quantum mechanical point of view, the simple system that describes all of your material, all your mineral, is the unit cell. Because if you repeat the unit cell in space, you obtain the whole object. Okay. by translation. So the overall properties of your mineral are given by the unit cell. So another reason of the importance of crystallography. The most important description choice here is the dynamical equation. So in the classical mechanics, we have the the Newton equations describing the forces interacting between the particles. In the quantum mechanical world, for small and light particles, we have the Schrodinger equation. Okay, Schrodinger equation is the description that gives the description of the forces. Very briefly, while classical mechanics is deterministic, so you have a formulation and you can in a determined way know where the particle, where your system is, how it is moving. In quantum mechanics, the solution of the dynamical equation is probabilistic, meaning that the interpretation is deterministic, but the solution is probabilistic. Quantum mechanics, the Schrodinger equation was obviously developed by Erwin Schrödinger at the beginning of the of the 20th century. It describes the particles in terms of kinetic energy and potential energy between the atoms and the nuclei and electrons. There are different ways of describing this formula. It is an eigenvector eigenvalue equation. I'm not going into much details onto it. Most important feature is that the only system for which the Schrödinger equation is analytically solvable are the hydrogen atom, which has one electron and one proton, and the helium atom, if we consider that the electrons not as two particles but as the center of mass of the two electrons. For all the other systems, for all other atoms, and for all the other system molecules, systems, solids, we have to introduce different kinds of approximations. One interesting stuff that maybe you studied in chemistry, during your bachelor degree, is that maybe you remember the quantum numbers. They are the solution. The quantum numbers comes from the solution of the Schrödinger equation. So you have the description of the orbitals. The orbitals is the region of space where it is the maximum the probability of finding an electron vibrating. So you can see probability, not the position of electron, probability of finding the electron. Two main approaches in quantum mechanics, some related to the wave function, okay, so the construction of wave function based on the Hartree-Fock theory, and some of them based on the electron density, so the density functional theory. This is a joint towards crystallography because the electron density is an experimentally observable, okay, that can be studied by X-ray diffraction. And we have, these are the two best known at the moment methods for wave function methods and time-dependent methods. Okay. Going straight to this slide here. So you have to choose for an atomistic simulation your model. Okay, your model. What is your material? The way you describe your atoms. Okay, the so-called basis sets that describes, for example, the electrons. Describe the electrons inside your material. The operator, the Hamiltonian operator, that can be from the wave function theory or density functional theory, or more approximated method, okay? And you can obtain, by solving the equation, the Schrödinger equation, and making some post-processing analysis, you can obtain several results. You can obtain the crystallography, the crystal structure of your material, study the crystal structure, atomic scale of your material. You can obtain the infrared Raman spectra, so you can compare it with your experiments. You can measure the elastic properties. You can study the thermodynamic stability of your materials. So you can see how your material interacts with the particle in time. Okay. Surface properties, interaction between a crystal and a protein, for example. Many kind of many kind of studies. Let's go to some examples of these methods in mineralogy and biomineralogy in particular, starting from the bone tissue. Okay, bone tissue, some of you coming from biology are well aware of the hierarchy of bone tissue. If we start from compact and spongy bone, we have some size of our components that we go down, seeing osteons and aversion canals. Osteons and aversion canals are made by smaller components that are collagen fibrils. Collagen fibrils are made by two components that are collagen triple helix, tropocollagen, also called, and biological apatite nanocrystals. And you have a composite. Your bones are made of a composite material, organic and inorganic, made of inorganic and organic components interacting together. Okay. So let's see something about the crystal. Okay. The crystals in our bone tissues that are made of, say, hydroxylapatite or hydroxyapatite. Other names are acronyms are given here, HA, hydroxyapatite, or hydroxylapatite if you want to be more mineralogical, and OHAP. And the unit cell formula is given by this term here. And the system is hexagonal with this crystal, with this space group, P6 on M. And it is nice to see from a crystallographic point of view that there are some cards that are called cards, CIF cards. The CIF stands for crystallographic interchange format. This is a textual representation of the system. You have your space group, you have your lattice parameters A, B, C, alpha, beta, and gamma, the space group, and the position of the atoms. It is interesting noting that the OH group here are experimentally determined, have a strange column here, OCC. It stands for occupation. And you can see here that they are within this space group. They are they occupy half of the sites. If you take this crystallographic file and put it into any kind of molecular visualization program software, there are some of them that are freely available in internet. You can see a structure like this. Look here. Can you see here the atoms that are cut in half? These are oxygen and hydrogen. This is a non-physical representation of the system. If I want to study it by a simulation, I have to make a choice. How do I orient these hydroxyl ions? I reduce, because modeling cannot deal with partial occupancy. So I have to make a choice. And for example, I choose this kind of orientation. It is equivalent if I make it in the other way. But as you can see, here, the symmetry should be from P6 free over M to P6 free. This over M here is an error, sorry. Okay, and now you can see that the number of atoms increased. Okay, I do not have any partial occupancy, but the number of atoms went from 7 to 10. Okay, the simulation, this was simulated quite recently, and the simulation that I have performed were made using the density functional theory of electron basis sets, a very fine and a very accurate functional that describe it. You can see here that there are very small variations in comparison with X-ray diffraction, so experimental determination of the position of the atoms. Here is the results. You can also see the difference by using different kind of models, physical models that describes my system. Here I used an all-electron basis sets, that is very nice in comparison with the experimental results. A less nice comparison is made by if I made some further approximation on the calcium atoms. And you can see here that the lattice parameters are different, have an increased difference in comparison with the experimental data. Okay. Okay, so it is said that the hexagonal polymorphs of hydroxylapatite is present in our bones tissues. Okay, but from a thermodynamic point of view, the hexagonal polymorph is unstable at room temperature and at a physiological condition. Okay, it is more stable at monoclinic phase, where you can see here monoclinic phase as a longer unit cell, an elongated unit cell, where you can see here two orientation, an up and down orientation of the hydroxyl groups in the different calcium channel here. Okay, whereas in the hexagonal polymorph they are intermixed. Okay, but actually they should be on the same direction. So the hexagonal polymorph is stable at 200 degrees. How can our body stabilize the hexagonal polymorph? By entropy, by including entropy, by including defects in our structure, defects in the hexagonal hydroxylapatite that are aimed at stabilizing our structure. In fact, with respect to hydroxylapatite, enamel, dentin, and bone tissues have a very different content, for example, of calcium and phosphor. There are some calcium deficiency. There are cationic substitutions, cations substituting the calcium ions, or anionic substitutions, such as the most important one is the carbonate ion. Okay, and biological apatite has actually this formula here, where you can see that several substitutions occurring at different sites for calcium, phosphate, and hydroxyl atom. The most important anion substituting the carbonate that enters into the structure, you can see here, is the carbonate ion that is 3%, 6%, and 7% in the enamel, dentin, and bone, respectively. So, being an anion and having two anionic sites, the carbonate ion can either occupy the sites occupied by the hydroxyl group, can substitute the hydroxyl groups, or the phosphate groups. In the first case, we have the so-called type A substitution or defect. In the other case, we have the type B substitution. Obviously, we do not have only A and B, but in nature, in a physiological condition, we have a mix of them in the so-called AB substitution or AB defect. So we have both type A and type B substitutions in bone. Regarding the type A substitution, we studied these substitutions with theoretical simulations to decouple the effects of the type A substitutions and type B substitution to see what happens to the crystallographic properties and other properties of the mineral when they occur in the hydroxylapatite, and then we recombine them to see the overall effects of the type AB carbonate defect. So starting from the type A carbonate hydroxylapatite, obviously there are some difference in the hydroxyl charge and the carbonate ion charge, so we have to compensate this charge imbalance because the materials are inherently neutral, so we have to restore the charge neutrality, and we made it, for example, by removing the other hydroxy group inside the channel. So the final formula for the type A carbonated hydroxylapatite is that one. A very interesting feature that puzzled the experimental crystallographers was how what is the position, the orientation of the carbonate ion inside the structure? The question is it a closed configuration like this one? So here we have the crystallographic C direction, and the carbonate ion is oriented in this way, or is it an open configuration? So with other orientation in space, or a planar configuration. Planar configuration is represented here in this model. So you have the carbonate group parallel to the AB plane. Okay. The question arises because at experimental level, the space group determined by the crystallographers was P minus 3. And how could it be? So, from our simulations, we observed that the closed configuration is the most stable one from the energetic point of view. And the open configuration spontaneously switched to the closed one. And the planar one is stable if we fix the space group, the symmetry. We make some symmetry constraint in our structure, but if we remove this symmetry constraint, it switches also to the closed configuration. So, what is the origin of this P minus 3 observation? Disorder in the structure. This carbonate ion is able to rotate within the channel with almost no energy barrier, so it is able to rotate inside this channel. We studied this by static simulations and dynamic simulations, how the carbonate ion orients itself in the structure. We saw that there are very small variations in energy between the different models. So the experimentally determined structure is a disordered structure with partial occupancies, and we observed that that is due to these different models. These are like different pictures of the channel of the carbonate ion position inside the mineral. Regarding the type B substitutions, we consider a physiological physiological way to restore the charge neutrality according to the chemical composition of biological apatite in bone tissues. We observed we substituted one calcium ion with sodium to restore the charge neutrality. We studied different models because of different symmetry in a biological apatite. Okay. We found the preferred position of the carbonate ion inside the structure, and we made, here you can see a comparison between the different models of hydroxyl apatite, different theoretical models related to the type A, type B, and type AB carbonate hydroxyl apatite models in comparison with the experimental determined structures. We can see that there is a nice agreement. There is a nice agreement, for example, for the type AB for this sample here with all the other experimental determined structures. Since the carbonate ion is one of the most present substituting groups in biological apatite, one of the methods to assess the presence of them and quantify the presence of type A and type B defects is by infrared spectroscopy. Why? Because we can see the signals of the different carbonate groups. We'll see it later. Here you can see a simulation of the Raman, of the infrared here, and Raman spectra of hydroxyl apatite. The solid line is regarding the simulation, and the dashed lines is an experimental results. There is a quite nice comparison between the experimental modes and the theoretical model and the real world samples, the experimental analysis, and we can see the power of the simulation here is that we can assign specifically each signal to a specific vibrational mode. Okay, we can see here a table related to the different modes for type A carbonate apatite in the simulation and in the experimental results. Type B, you can see, and the type B carbonate apatite, you can see here that the stretching modes have a very different wave number according to the position occupied by the carbonate ion. In the channel, in the calcium channel, you can see here the position of the peaks. This is between 15 and 16 hundredths reciprocal centimeters, and in the carbonate apatite, in type B defects, it is between 13 hundredths and 14 hundredths reciprocal centimeters. And going forward, you can see here what happens. What actually happens at the experimental level, you can see it here. You can see here the presence of different peaks depending on the type A and type B carbonate ions. So at the experimental level, it is measured the amount of type A and type B carbonate ion content according to the different intensity of these signals. Okay, and the peak are shifted to the site according to the site occupied. Another interesting thing is that this one, we calibrated the response of the Raman signal of hydroxyl apatite according to the different stressing condition of the mineral, finding different modes. For example, these are the modes. Sorry, these are the stretch. They are the straining, different strains applied to the material along the A axis or along the C axis, and we can see that the modes, the most intense mode here is the symmetric phosphate band, and it deeply changes according to the stress, to the applied stress. Whereas if we consider this kind of shear stress, we do not see a variation in the position of the peaks, but just a variation of intensity of the signal. So we have a response. And if we can calibrate this position according to this piezo spectroscopic parameter here, we can calibrate the response that we can calibrate the position of the signal of the Raman band, the symmetric phosphate group stretching mode, according to different stress in the material. And in this case, it is what it has done at the experimental level to map the residual stress in the bone tissues. What you can see here, this is, for example, a collagen. This is a cortical bone sample that was analyzed on one side here to calculate the collagen volume fraction. Okay, so, and here you can see the position. You can see a map that correlates, that is a correlation, okay? The correlation between the position of the Raman peaks and it was translated into a residual stress. And you can see here that is something in the cortical bone, something like a crisscross stress field. You can see here that there are some bands at high pressure, at high stress values that are along specific directions. And another very interesting feature is this one, okay, that is related, it was measured by Professor Pezzotti at the University of Kyoto. He studied the dentin enamel joint called DEJ here. So you have one signal here, according to stress, and he measured the variation of the stress inside in this joint according to different stressing conditions. And something that is very interesting is that there is at no applied stress, a tensile stress in the enamel, a compression stress, sorry, enamel here, and a compression stress in the dentin core, and the interface between enamel and dentin is stress-free. The stress is zero, and it doesn't change this stress-free zone when you apply a stress. So when you use your teeth to crush food, the joint between the dentin and enamel releases the stress between the two components. Okay. Okay, I guess it is. I'm done. If you have any question, I'm sorry for the delay. Unfortunately, we had some issues during the trip, during the road here. If you have any question, please feel free to ask. I do not know if there is any question from the virtual classroom.
Raman Spectroscopy is
Pardon, put down the mask.
Spectroscopy is for analyzing contaminants in marine water.
Depends on the kind of contaminants, because if it is for example, an organic pollutant, it could be used. For ions, no, because ions are spherical, and the polarizability of a sphere is isotropic. So you cannot change the polarizability, and it doesn't. You cannot measure the variation of polarizability and a Raman signal from an ion. But if you have some nanoparticles, maybe yes, it depends on the kind of systems. Microplastics, okay. This is okay. This could be because they are macroscopic objects from an atomic perspective, so they could be detected. It depends on how much material you have, and if you can, for example, condense it, you could analyze it. Also in solution, because one powerful feature of Raman over infrared is that the signals from water in Raman spectroscopies are smaller, whereas in infrared spectroscopy you have a very broad signal coming from the solvent, so you cannot use water in the.
More selective. Raman spectroscopy is more selective.
No, is less sensitive to the presence of water. It's different. Okay.
Any other question?
The technique is I think the sample can be unique by the laser.
Okay. It depends on the configuration of the instrument. For example, in confocal Raman microscope, it is not destructive unless you want to see specific features. So, for example, to cut your samples, polish your samples. So in this case, could be destructive. But in that case, no, it is not destructive. But it depends also on the power of the laser. If your laser is has too much energy, it could cause photo bleaching in your material. It depends. In this case, it depends. One have to maybe sacrifice a sample to. Okay. Yeah. Okay. It could be, in that case, maybe you can start from a long wavelength laser. Then, if you need more signal, you can try to increase the sorry, to reduce the wavelength of the signal. So you may start from a near infrared laser and then go up to red, yellow, green, and so on.
Okay, well, thank you, Gianfranco.
Thank you very much.
We hope that this morning we had the chance to see that our crystal could grow and our crystal could be measured. Because what often happens is that maybe you have to do with some material which is in a condensed state, which could be open. And you can measure with instruments the signal which comes from the crystal, and the signal could be affected how the crystal is made and how the crystal is organic. So you need to know how the crystal is made, not only as a basic knowledge of crystallography, but also to understand your sample and also to understand how your instrument is working. Because the simulation allows you to understand how the crystal is made and all the signals should be after the simulation. And you can introduce defects inside the simulation, so you can introduce entropy. And you can get closer and closer and closer to your natural sample and what you expect from your instrument. So you need the sample. So thank you, Gianfranco.
Thank you.
And the next lecture will be at 2:30. Okay.
Thank you, Gianfranco.
Thank you, Stefano. Ciao.
Excellent. Thank you. Interrompi registrazione, sì, lo posso fare.
Ok, perfetto.